Hello, welcome to the stream. Welcome to the last episode of the series Learning Amiga 68000 with Docster. So, please like and subscribe my YouTube channel. It's the only way I know of, sharing what I do and getting more people into game dev. Let's say that, related to Amiga. Remember that under each video there is this more thing, and normally you get links to where the code live if it's related to some source code. All the source code is on Mega. You'll get the link that takes you there. You might need to register to get access to the code. Please like and follow my Facebook page. Oh, that should not be there. My Facebook page, it's my blog, and I will be updating this. Now that this series is finished, or is the last one, all the streams that I will be doing will be game dev. There's no more teaching stuff in a way. It's just game dev. And there will be the occasional, let's say, there will be the occasional where I cover some topic, but most of the time it will be game dev now. Like the blog, I have a Facebook group, Phase 101. Please join that group. And the famous Commodore Dev Facebook group also. So this group is getting quite interesting. It's growing and growing. So please join the group and follow anything related to Commodore there. It's of course related to Commodore, whether it's 64 or Amiga or any other Commodore machine. If you send me messages, let's go here. If you send me messages on Facebook, I do read them, but I take my time. But if you send me on Discord, so please join Discord, I will reply to you more quicker. So just join my Discord group. The link in the upper right hand corner for Discord is wrong. Somebody brought this to my attention last week. I need to update it, and actually I will change the upper right hand corner thing that I have there. From now on I will just have Linktree there. If you don't like Facebook messages, message me on Facebook. If you don't like messaging me on Discord, you also have the option of going to Telegram. You can join the Telegram group and you can send me messages there. That is also, you also get a quick reply from Telegram. For those that want to go the extra mile, and support me or support us, you can join the Patreon or Coffee. Okay, both of them has got development videos. In this case, you're going to unlock 106 videos related to game dev or Amiga dev, let's say that. Um, which these videos are not on YouTube yet. If in future they will be, but they take time. Also for my Patreons, I have about 6 or 7 videos that are going to go in tomorrow, I hope. So Coffee or Patreon, guys. Also, I need to remind you of the Phase 101 Retro Programmers Inside Game Jam. It's the Tanks Game Jam. If you want to join and submit a game to this jam, you are more than welcome. It can be Amiga, it can be anything, any retro machine. Read the rules, you'll find out. There is also a sentence that you need to add, which is this one. And these are normally the processors that are accepted. So any retro machine that has got these processors will do, given that there's an emulator for it. And you tell me how to use the emulator. So please also provide some kind of documentation for the next game jam. Also, if you want to see all the games for the jam, you will find them on the Retro Programmers Inside HIO webpage, those that were released. So let's go to what Docster provided. So today, guys, is real revision. I will be a bit fast in terms of what I will do. Some of these examples you have already seen them, because in the beginning I started using them, but then I decided to do a whole episode of them. So it's literally a revision of everything. So guys, let's start. So we're going to start from the zeros and ones, okay? It's a lot of text, this one, but we will start from then. So we're going to start with the bits and of zeros and one for for today, exactly as we started basically in the first episode. On the first episode, I was going through lots of stuff. So nibble is for bits, okay? And as you can see, we have for either 0 or 1. Byte is 8 bits, which is composed of 2 nibbles, okay? Word is 16 bits, which is composed of 2 bytes or 4 nibbles. Long is 32 bits, which is composed of either 4 bytes, okay, or 32 bits, of course, or 8 nibbles. So before we continue on our tutorial sets, we need to dig more into bits after the previous bit set, bit change, bit clear, and bit. This will not be a long presentation, so I'll keep it very short. I mean, these are the words of Docster. Now, please note this this text, he wrote it in the middle of his series, but I decided to do it in the in the beginning of the series. What did you say? 8 bytes? No, it's 4 bytes. I guess you are talking about long word, no? So, least significant bit in a byte, it's always bit 0, okay? In a word, it's always bit 0. In a long word, it's also bit 0. You will notice that all bits are 0, meaning they are all cleared well, except from one bit. Okay, I mean the English of Docster here is not quite clear. The furthest to the right is set to 1, meaning this bit is set. This is referred as the least significant bit, also known as LSB. So basically, the first bit, bit 0, is called the least significant bit. The most significant bit is the last bit. Okay, so if we have a byte, it is the 7th bit. If we have a word, it is the 15th bit. If we have a long word, it is the 31st bit. Remember, we start from 0. Practice usage. The term LSB and MSB, yeah, that's one thing that I forgot to mention. MSB is most significant bit, and it's also the leftmost bit of any byte, word, or long word. Is used everywhere. Okay, you will find LSB and MSB everywhere in manuals, hardware reference manual, etc. All other programming languages, of course, all other programming languages that use binary manipulation uses these terms. This is why it's very important to know about these things. It is also important to know this. No matter what size, byte, word, or long word you are using, the LSB and the MSB will always be the same. Furthest to the right is the least significant bit, and furthest to the left is the most significant bit, as I said. To make this easier to remember when working with bits, is that bits are read from left to right, okay, beginning the count from 0 and up. So this is the we start reading from the right side and we go further to the left. Okay, so this is bit 0 as Doctor is indicating, and this is bit 7. Okay, these numbers mean the bit number. Sorry, right to left. Sure. Yeah, that's my English today. Yes, thanks, SP. Yes, you start from the right and you go to the left. So, he gives an example here, which we will cover later on, okay, about clearing a bit or setting a bit. I will cover it later on, so I won't be doing that. Okay, that is binary number. Okay, we have a binary. How can we convert it to a decimal? Converting a binary number to a decimal is quite easy when you know how. So we know that we start our count of bits from the right side to the left side. So as he showed here, okay, and as we've seen it before. So how do we continue? Well, to do this, we need to start with 1 and adding the number by itself. So if you notice, okay, the numbers are to the power of 2. Okay, so 1, 2, 4, 8, 16, 32, and 64, and it continues like this. So what he means is we start with 1, but 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 4 is 8. 8 plus 8 is 16. So it's always to the power of 2. This is what we have now. So basically, we have this binary number. These are the bits. And we just, where we have a 1, we add these. So here we have a 1. So it's 1. Here we have a 1. So we know it's 8. Here we have a 1, so we know it's 16. Here we have a 1, and we know it's 64. And we continue like this. Here we have a 1, it's 1 to 8, and so on. So we are only calculating the bits that are set to 1. Okay? And let me correct that is, it should be R. Okay, so that was binary, okay? So I guess most of you know this. And I'm going to change to the next example, okay? Give me a second to... And also give me time to... Hello, Berkam, whatever, I cannot say your name. Welcome to the stream and thanks for the follow. I do 68,000 assembly. I'm covering the 68,000 CPU instructions.
Yes.
And also I do Amiga game dev. Next streaming series will be Amiga game dev. So next Sunday, it's game dev for sure. Stretch. You want me to stretch? But thanks for the follow, Berkam. It's very difficult to say your name, so apologies. Anyway, so tutorial 1. We have seen this one, okay? So let me execute it without running though. So actually, before I do that, I want to show you something here. So at line 97, we have a warning, okay? Why we have this warning? We are doing move quick 80, D5 into D5, okay? What we actually will be transferring, I mean, remember, quick is always, move quick is always long. There is no move quick word or move quick byte. So a byte, okay, which is 80 in this case, has got the most significant bit set. Because of that, the bit gets extended through all the 32 bits, okay, the remaining 32 bits. So remember this, the assembler gave us a warning that is changing it into this, okay? Maybe we did not have that intention, but it did it because it has this AI built in. I like to use this word AI, okay? Yes, assemblers do have AI. So let's go through the tutorial. So first of all, remember that move can do, okay, byte, word, and long word, okay, except when it's move quick, okay. If the size is not defined, also remember it's always a word, okay. So I always encourage you to use this size. Don't skip it. I was lately enjoying the Discord group where they cover a number of CPUs. I mean, they cover 68,000, they cover Intel, they cover RISC, ARM, and all that stuff. But I've seen some of the code, and they are using the 68K simulator, okay? Most of them. And I've seen the code that they and some people right there for um, issues, okay, and to help them out. And I helped somebody recently, I mean this week, seeing his code. One of the issues he had, okay, is because he was always not specifying the size. It will get you if you don't specify the size in 68,000. Even when you're looking at your code, it gives you a better understanding of what you wrote, okay? So always specify the code. I'm not going to beg, I'm not going to tell you please do it. It's up to you, but I'm suggesting to you that if you don't do it, you are more prone to error, okay, to have bugs. So here, okay, these 4 instructions, okay, we are moving f's, okay, a 32-bit number, which is f's, into D0, D1, D2, and D3. And you're going to see it in the assembler, in the debugger, with the numbers being populated up here, okay? Now, this is something that I want to cover at a later moment, okay? In this same group that I saw, that I am in, okay, Discord group, somebody suggested that if you do the 0 to D7 slash A0 to A6, okay, it is slower than doing D0 to A6. I can assure you that is not the case, okay? They mean the same thing, okay? And I will show it to you in a minute later on. I changed this example, this tutorial of Docster. I changed it with this update. So when you're specifying move m, when you're moving things to the stack, okay, whether you specify D0 to A6 or you divide the data registers and the address registers, as long as they are all, okay, from D0 to A6, it's always the same. It always takes the same time, okay, no matter what. It's a way of writing it. That's what the difference, okay? That's some people prefer to specify D0 to A6, and some people prefer to divide it, okay? It doesn't matter. It's still the same. What matters is how many registers you specify. If you specify D0 to A6, then it takes a lot longer than if you specify D0 to D7, for example. So do not get confused by the how you write it. It's only by how many registers you specify. It takes time. Yeah, SP never call an assembler a compiler. It's not a compiler. It doesn't generate code because that's why it's called an assembler. I'm not trying to correct you. I know, I'm sure you know, but an assembler is an assembler, not a compiler. A compiler converts high-level language to assembly, while an assembler doesn't. It doesn't add code. Never does. Look, Hound Dog put my quote. Good one. This I'm correcting you because young ones confuse this quite a lot. The younger generation cannot distinguish between an assembler and a compiler. They think they are the same. So here we're going to move all the registers except of course the A7, which is the stack pointer, to the stack. Then we're going to clear the registers D0 to D3, and then we're going to get them back, as you saw. However, we did save all the registers and we restored all the registers. Another quote, assembly is core. Yes, it's core. So now we're going to talk about immediate mode. We are going to move 10 into the 0. Okay, now notice the move doesn't have we didn't specify the size, but it's a word. Okay, so look how many nibbles or how many bytes are going to be affected in the 0. As you saw, 2 bytes, 4 nibbles. Now we're going to move a byte into the 2, okay? Into the 1, sorry. And notice how many bytes are going to be affected, or how many nibbles. Of course, it's a byte, so it's a byte, no? And we continue like this by doing word and by doing, so move.word 10 and move without specifying the size. 10 is the same. As you can see, the 0 and the 2 are the same. And the last one, move.long 10 into comma D3. As you can see, we affected everything. Okay, let me see what Docster wrote, because I'm not reading all his comments. Result, move.long 10 comma D3. Result this time will be, this is the same as doing move quick. It is the same. Why it's not correct, SP? He's saying move.long and move.quick, it will be the same. It's not a negative number. Okay, fair enough. So now notice move quick 10 into D4. Okay, notice that we end up with the same like D3. Well, he specified hex, sorry. While before he was specifying the decimal, but it didn't affect the rest of the bits. Now we're going to do move quick 80 comma D5. So you can see that it affected all the other bits because we have the sign bit extended. Now move long D0 comma D3. So we are moving the contents of D3 into the contents of D0 into D3. So here we have that example of the hello world. Okay, so we have a text string and we are moving the address of where it starts into 80. Okay, so you can see 80 points to our string. However, notice that we specify hash in front of the label. So that means the address of the label. Okay. Now, if you don't specify hash, it means the contents at that label. So we are moving the 4 bytes where the label is into 80. Okay, and notice what's going to happen. We get the 4 letters that there are in our string, which are HOWD. Now, let's start again and let's get the address of hello world into 80. Okay, we are going to move the byte at 80, so this time we're only moving 1 byte, okay, into the 0. And you can see we get the number 48. So same number that we had before we overwrite 80. And then we're going to move, okay, and this is interesting, okay. Here we don't have a number in front of the 80. Here we have, these mean the same thing. If you don't specify the 0, it means you're moving what there is in 80 into the 1. So they will be identical. Okay, 48 and 48. Ignore the rest of the bits because we only moved a byte in both cases. Now, if we move dot byte, this time 4, so we had the word howdy, if I remember correctly. Let me look into my notes because I cannot, I have to stop the assembler to show you what there is. Yeah, it's howdy. So 4 is the letter Y. Okay, so we are moving the letter Y, the ASCII of the letter I, into the 2. And that is 79. Now he's going to teach us, Docster, the addressing mode with increment and decrement, basically. So if we move byte 80 plus comma d1, so we take what is in 80, we move it into d1, and then we increment a1, d1. Sorry, we take what's in 80, we move it into d1, and 80 gets incremented. And you're going to see that 80 increases to 13 at the end. Remember, we're moving a byte, so it will increase by 1. And you can see it increased by 1. Now, we take what's in 80, okay, and we move it into D1. Okay, so the next word, which is O, the next letter, sorry, which is O. And we increment it again. So it became 114, and we got 6F. Now we have post decrement, pre-decrement. So we decrement first, then we take the contents of 80 into the 1. So we are going backwards now. So the 114, this number here in 80 will be 113. Okay, and D1, okay, will be the next letter, which should be, I think, 48. Was it 48? No, 6F. Oh, because we moved. We get again 6F. So we are going to go backwards again, and we're going to get the previous one that we had before, the O, which was an H, and that was 48. So we're going to get 48 into the 1, and this will be 112, the start address of 80, where we started. Right? Now, we are going to loop here, okay? So yeah, I skipped from 198. So we have buffer, the address of buffer, into A1, okay? We move what's in A0, okay? We increment it, and we move what was in A0 into A1, and we also increment A1. So we are doing a copy now, okay? And we copy again from A0 to A1, and also in both cases A1 and A0 are incremented. So we're going to continue to see when I execute this one, okay? When I execute this one, that is going to copy what is in 80 into A1, and both of them increment. So it's a repetition of what's in line 207. So this type of copying with increment, okay, we can do it with a loop, no? So let's get the address of the label where we have hello world, where we have the source string. And let's get the address of the buffer where we have the destination, where we're going to copy our string into A1. So we have source and destination. Let's get the length of our string into the 0. Okay, so the 0 will tell us how long is our string, and you see it says C. Okay, now we're going to copy with a loop what's in A0 into A1, increment each time, and we continue and we decrement the 0, so line 222, okay, we decrement the 0 and we loop back to line 220, okay, which is actually instruction 221. So we're going to do this all the time till we have till the 0 is equal to 0, okay? So we were copying. So notice we did also 0, okay? And we exited. Now, there is a bug there, which I had corrected in the previous episode, and I haven't corrected it here, which I will show you in a minute. Why? Because it does the 0, the length should be, okay, where we specify the length, okay, hello world len, okay, should be hello world len -1, okay? So that is a bug, but anyway, it's something that it will catch you up a lot, okay? Anyway, we exit, and now we're going to read the table. How can I show you? Maybe if I do this, because you are not seeing the tables, no? Let me see if I manage to show you. So before we had this this string, and we copied it to buffer, okay, we copied it to here. One thing, this is also something that I had corrected, that if you don't specify, that will be a word. Another one which I did correct is the even. Docster did not have the even directive here. Make sure you always specify the even, okay? Because these are things that will catch you, okay? So, yeah, don't worry, Docster. I mean, I'm not trying to find flaws in what you did. I'm using what you did to, you know, show issues that, I mean, you were caught in them, and anyone else can be caught. Even I will get caught in them. So just to make you aware. So we are going to read from a table. So we are going to get the address of the table into 80, right? We are going to multiply 4 times 4, okay, which is 16. And we're going to move 16, the the long word at 16 into the 0. So notice what we're going to have in the 0. 16. Now we're going to add what we have in the 0, which is an offset, to what we have in 80. So 80, which is the number that ends with 146, we're going to add 16 to it, which is 156. Okay? So D1 will have that value, which is what is in line 273. Right? 274, sorry. 1, 2, 3, 4, 5. Yeah. So if we want the next number, so the addressing mode, we can specify the address plus an offset plus another offset. Okay, this is how it has a name. It's a very long name, but this is how I know it. Okay, the address plus this offset plus this offset. Okay, both of them are indexed in a way. You can change this or you can change this, but you cannot have a register here. Okay, this can be a value that you specify, and this can be a data register. So now we end up with what is in 275, I believe. Yeah. Now here I'm going to talk about what I spoke earlier about the address, the move M. Okay, and the best way to show you the move M is by doing this. First of all, I'm going to switch on the counters. So we have the move M instruction, okay? And we have move M dot long D0 to A6 or move M dot long D0 to D7, A0 to A6. Notice they are identical. 1 to 8 cycles, 4 bytes. Okay? That's what it means. Same thing when we are restoring from the stack. Okay? It is 132 cycles, 4 bytes. No difference. Okay? And what I want to do, I'm going to execute these and exit. Okay? But what I want to do is disassemble. So, I had to assemble and disassemble, assemble, disassemble. So let's find the move M's in our program. Here they are. Notice there are the same instruction for E, for 8, E7, okay? And with the bits specify the registers, okay? So FFFE, and same thing for the other one. And same thing when we are restoring from the stack, it is 4 bytes or 2 words. The instruction opcode is for CDF and then 7FFF for moving the registers for in both cases. So it doesn't make any difference. I hope that is clear. Okay, so back to the Amiga now. And let's do the next. Oh, read, continue. And let's do LEA. Guys, I hope I will be able to do them all because I'm realizing I'm taking long. So, again, first of all, at the top, we are defining some library offsets. So we have -198 and -19E. You get these from the Amiga reference hardware manuals. They also have names. People that you see use the names. In assembly, you can also use the name, but I think most people get used to use the offsets. But if you want, you can still use the name. Yes, that's what it is in the end. He's also using other equates, let's say constants, for file handler and length of a file, etc. So just to make you aware that these are constants, what we have here. So we are moving everything to the stack, all the registers to the stack. We are getting an address, okay, of, now remember we are using LEA and not move. So LEA always returns a 32-bit address, load effective address it means, okay? So, and the destination is always an address register. Well, it can be a data register. Actually, that's a good point. Because I might be confusing you, but it's always 32-bit, that's for sure. Right now, I got confused myself. Let me check to be exact. No, LEA is always an address register. Yes. Yeah, I thought it is, but for a moment I thought it can be a data register. Sometimes you get this lapsus, no? So, and address registers are always 32, okay? So when you're passing an address, that's what I mean. You don't pass half of an address, a word, you always pass a full address. So we get the address of text into 80. We move the byte that is in 80 into the 0, and we increment. And we move the byte into 80 and we increment again. They do the same. But move lets you move the address to a data register, while LEA will not. Speed difference. I don't know it by heart, but I can check it for you. Let's do. Give me a second and I will tell you. LEA. Immediate. LEA text. 90. Long. Right, and it could be capital T, capital T. Okay, so let me switch again. So you can see on my right side, I wrote these two instructions, okay? I'm going to toggle the counters. You can see both of them take the same amount of time and the same amount of cycles. Both of them is 12, and both of them are 6 bytes. But I'm going to put another one, okay? LEA text bracket PC comment 0. This is faster and shorter. It's 8 cycles and 4 bytes, okay? Because the label is relative. So it is faster as long as the code is in the same section, okay? Because you cannot use the PC, you cannot use PC relative unless you are, if you are in a different section. I'm going to actually move them just before here, so the example will be complete. And let's say hash, sorry, not hash, these two are the same. And this one faster and shorter. Okay, so this example also shows how to handle libraries, okay? So to open a library, you always need the exec base, which is address 4, okay? So you move what we have in address 4 into A6. We want the DOS library. We are specifying it down here, okay? So we pass the name of the library into A1, and we call the old open library A6, okay? It's specified in those constants. The old open library is specified in those constants that we had before. When we open the library, we Why is it? Oh, I jumped into the open library. Sorry guys, I need to start it again. And go to where we were here. So we get the address of the library into A6 and we make a copy. Sorry, we get the address of the library into the 0 and we make a copy in the variable or memory location that we called DOS base. Okay, now we're going to move what we have in DOS base. That's hello from Amiga into A1, and we're going to call the system routine output file, okay, which outputs things to the console basically, and we move the 0, what we have in the 0 into DOS out. So we also get the handle out. It's a handle. The comments are not exactly correct, but I left them as Docster wrote them. Okay, so just bear with the example. Okay, don't take literally what there is written related to the DOS. So we get the handle. We store the handle into the DOS out. Now we take the DOS base, because to call any system call, which is a DOS call, you need the DOS base, which we got stored in the variable called DOS base, and we have it into A1. Then we have DOS out, the standard file input output, and we move that into the 1. Then we take the address of the string, which is text, okay, and we move that into the 2. Then we pass the length of the string, okay, and which is, if you can see it on this side, okay, we have text end and text, okay. So if we do this label minus this label, we get the length of the text, and then we call the library routine to write the DOS write, and it writes this to the console. Of course, here we are not seeing, we don't have a DOS console, but if I had to open the shell and run this program, it will do that, okay. Then we do move long DOS base into A1. So now we are going to close the library. You always have to do this. No, you have the address of the library, you pass it into A1 because that is what required, and we close the library, and then we restore back. Okay, now you can see here that I have actually generated the exe of this file. So I'm going to go to the shell and show you that it does what Docster is saying. So let's run it. Yeah, yes. I'm using Visual Code to explain the code in a way and writing my notes, but actually everything is in Asm Pro. I'm just sharing the directory between both. I'm not using the extension of Asm Pro. So it's 202.exe. Okay, guys, we're going to execute it and make the window bigger. This is not Windows, guys. It will not let me make it bigger. That's the font. And if we run it, you should see hello world. Definitely not. Definitely not. The screen actually that I can make, yeah, by doing this. But that's the best I can do, removing the visual code. So you can see the hello world. That's all we did. Now we wrote a string to the console. Okay, back to as in Pro. To be honest, I'm not using a very high res because of the because I'm streaming, no. But um, yeah, it's what it is. If I had to use a, I mean, I'm not using an RTG card on my Amiga. I'm just standard mode. What the OS 3.1 lets me, but that's it. So we did LEA and we move to the next tutorial, which is tutorial 3. So this one is using the instruction add, and add has add and add quick, and add quick can take a value between 1 and 8. Okay, it's not like move quick. Okay, it's add quick, so you can specify an immediate value from 1 to 8. So don't confuse the two. Okay, so we're using we're storing sorry, we're moving the address, sorry, not the address, the value that we have at my value into 80. I can tell you that there's a 1. Okay, so and we moved 1 into 80, as you can see. And now we're going to add quick immediate 8 to 80. Okay, it makes it now. Now notice, and I left this example intentional, okay, and not said anything. We are using address registers to do arithmetic, not data registers. This is a good thing, okay? It permits us, the CPU permits us to use address registers and data registers to do addition. So sometimes, I mean, I prefer to do addition using data registers, but sometimes you need address register and you also need to make addition on address registers. So it's a good thing that we can do both type of registers. Now we're going to do a move 80, what we have in 80, okay, which is the 9, into my value. So we're and now our variable, we're going to move 9. Now move.long my value into A1. And you can see we still got 9. So we got the contents of what is my value into A1. Now we're going to add 80 with A1. Guys, note you cannot specify byte with address registers. So we are adding, okay, 9 plus 9, and it goes into A1. So it's 12, which is 18. Now we're moving 1. Now we shift it, okay? We're going to use data registers. We are moving 1 into the 0. And now we're going to add 1 into A1. And you can see it became 13. So basically, you can use data registers and you can use other registers and you can mix. That's what's important here. So we go to the next, which is sub. So sub is the same like quick, like add quick. Sorry, sub is the same like add, and it also have like add, it has add quick, sub has got sub quick, okay? And it also permits us to use data registers and address registers. So it's the same example, but using sub instead of add. So we move the value that we have in my value into 80. Then it took the value that there was before, okay? Because we loaded another program and the memory doesn't get reset, no? So it took the same value that there was before. So we get 13. So we sub quick, unless he put 13, let me check. Actually, he had 13, so forget it. But normally the assembler takes what you had before. So just to make you aware of that too. I mean the assembler as in Pro, because if you use the extension of Visual Code, it will not do that. So 80 has got 13, and now we're going to subtract 8 from 80. So we end up with OB. Now we're going to move dot long 80, so the B into the variable, okay? And then we're going to restore it back into A1, okay? And then we're going to move 1 into the 0, and then subtract that 1 to A1. And notice it became FFFF because it was at 0 and we subtracted 1. So we can work on address registers, okay? That was sub. We're going to do div and divs. So remember the difference between divs and divu. One is signed, the other one is unsigned. They work with data registers, and there is a mistake there. In the notes, I'm going to correct it in my thing. It's not .l but .w. Here I have .l. That should be .w. Long is 68020. Okay. So for 60, don't mix it because this mistake you'll do it. Okay. As you can notice, as you notice, Docster did it also. I did correct this in the past, but that escaped me. So you divide a number. A number can be a long number, but you divide with is a word. Also, the destination can be a long number, so it's always the destination divided by the source, not vice versa, source divided by destination. Remember this, right, left, okay? So you take the number that is on your right, which is the destination, and you divide with what's on the left. So we are clearing the 0 and the 1. We are moving that number into the 0. And we are moving 2 into the 1. And then we are dividing the 0, that long number, with the 1. And the result goes into the 0. The original instruction of Docster was div_s.l. As per notes, div_s.l is not a 68000 instruction. It's a 68020 instruction. Okay, just to make you aware, especially, okay, if you write code on an Amiga 1200 and you want your code to work on a Amiga 500, because on an Amiga 1200 this will assemble and will have no issue, but on an Amiga 500 you will have issues. So when we do the division, notice we get the V flag. Why the number was not changed? Because we had an overflow, so the number is wrong, what we have in the 0. We could not, the CPU could not divide, okay? And the extended bit was also switched on. You need to be careful of this, okay? Now we have another number into the 0. We are also moving 2 into the 1. And now we divide that number with the 0. And you get the 4000 and the remainder is 1. So the division works like this. You get the whole number in the low word and the remainder in the high word. Okay, so 4000 is the whole number and the remainder is 1. Give me a second, guys. I just noticed something. Just to tell you something that I am correct, not inventing things. Okay, so from the divide instruction, we go and do, oh, I forgot to save what I did for the divide instruction. Okay, so we go to the multiplication. So here, Docster had the same issue that he had on the division. Multiply is always a word, not a long. Okay, long is for 68020. Okay, and also you have MULS and MULU, so signed and unsigned. So on 68,000 is .w, okay? If you are using 6802, you can use .l. And this is the same thing, destination times source, okay? Although the answer is the same, whether it's source times destination or destination, in division doesn't apply, but the CPU, what it does is always destination with source, okay? This applies to any type of arithmetic that it does. When it's doing a compare, when it's doing a subset, when it's doing a sub, when it's doing an add, it's always right, left, okay? Destination minus source. Compare, destination minus, because it's a compare, minus source. And that's where all things work. So, same thing, but we are using multiplication now. So we clear the 0 and the 1. We move 10 into the 0. And we move 2 into the 1. And this time assigned. So we multiply the 0 by what is in the 1. And we get 20. Now remember, because this is signed, we also are limited by the amount of numbers we can have, okay? Because the most significant bit is the sign bit, okay? So if that value, which we are going to see, we're going to move a number which is higher than 8,000, okay? So, and notice the multiplication, the number fitted, and the flags here, nothing is set, everything is fine, and x is set, but whatever. The value fitted, we have no issue, okay? Now we are going to do a move long with a value which is higher than 8,000. So that means we have a negative number times 2, because we move 2 into the 1. So we are going to multiply the negative number, the 8FFF, which I don't know what it is in decimal, to be honest, but minus something, times the 0, which is times 2. Notice the M flag is switched on, okay? The value is 1FFFE, and we have a remainder of FFFF. We do not have overflow, so the V flag is not set. So it fits. Sorry, I told you wrongly, because for a moment I was thinking in division. We multiplied the number, okay, the 8FFF, which is a negative number, times 2, okay, and we get the value FFFF 1FFFE, okay, not this is the whole number and this is the remainder. So apologies for that. This is the actual number, that 8FFF, whatever that minus is, times 2, okay? Okay, branches. So when I did the branch instruction last week, okay, I showed you a table, okay, of those that are signed, those that are not signed, and those that are common to both, like the overflow. Docster did another table here, which is a good one also. However, it doesn't tell you which ones are used for signed numbers and which ones are not used for signed numbers. But you can get an idea from the N, okay? These, where you have the N flag set, okay, these are normally for signed numbers. The V flag is for overflow. This is common to both, and the rest is for signed. My table is more accurate, okay? But this is just to give you an idea. What is good about this table is that he indicated also which flags are set up. Now, branches, okay, you can branch based on one of these conditions, okay, which you have here. So B and this CC, Docster had XX written instead of CC. I corrected it to CC because in all the books of the 68,000, it is CC, branch on conditional code register. Conditional codes, I forgot what it means exactly, but anyway, BCC. So DCC is replaced with one of these, okay? So you do a compare, and that compare, then you do a branch, and branch is based on one of these. The compare can be a byte word or a long word. A branch can either be short or long, or W, okay? A branch can be either word or, so it can either be -128 to +127, or -32768 to +32767, okay? So byte or word. We are doing branches here. Relativity is varies. Above those numbers, you have to use jump. So let's do what we have. So we are moving 100 into the 0, and we are and moving 25 into the 1. And notice that we moved words. We are comparing, it's also a word, the 0 with the 1. So this is like the guess the number, but he's pretending he's putting the numbers, okay? There is no random here, and no user input, but it's a good way of showing the instructions, the compare and the branch. So we are going to compare D1 with the 0, okay? Are they the same? Are they equal? If they are equal, we jump. So are they the same? It shouldn't be. So we go to next instruction. Is the 1 greater than the 0? Is it? It's not. So we should not execute that. Is it less than the 0? Sorry. Is the 1 less than the 0? It is. So we execute the less instruction. We jump to the less label, as you can see here. Now we multiply D1 by 2. Okay, so D1 becomes 32. We jump back to our loop. So again, is D1 equal to the 0? It's not. Okay, so we do not do it. Is D1 greater than the 0? It's not. So we do the next instruction. Is it less than? Yes. And we multiply again, and D1 becomes 64. We go back to the loop. Now we compare the 0, D1 with the 0. Are they equal? They are for sure now. So we execute the equal. The equal, we multiply D1 by 2, so it becomes C8, and we jump back to our loop. Now, we are going to do another compare, the 0 and the 1. Are they equal? Definitely they are not. Is the 1 greater than the 0? Now it is, so we execute the greater part, and of course we return to the OS with this one. So I hope that example shows the compare, and remember, right with left. Okay, so the compare is D1 with D0, not D0 with D1. Keep that in mind because it will get you. So we jump to a different topic. We're going to talk about clear, swap, negate, and no op. Okay, so no op, the computer does nothing. You just waste cycles. Okay, this is like what we have in 6502. Negate, this is important. It does a 2's complement of a number. So if it's a plus, plus 4 becomes minus 4. Okay, if it's I don't know, 100 plus 100 becomes minus 100. Okay, just to make you aware, negate is not like not. Okay, it does 2's complement. So we put 1 into the 0. Negate the 0 gives us the 2's complement of 1, which is FFFF. And notice negate is word, what we had there. I don't like it when Docster doesn't specify the size, but I left them there to make you aware that it's not clear all the time. The other, I should have also mentioned the other instructions. Okay, so we had no op, clear, so we clear a register or a byte, some memory. We swap, we can also swap high word with low word and vice versa. And the negate, which is the most important, which is handle sign numbers. And I should have written sign numbers there, so I'm going to write it. To complement. So we negated back. So what was minus 1 becomes 1 again. Okay, now we move this number into the 0. We move the 0 into the 1. And we also move the 0 into the 2. We copied it 3 times. We clearing it. We clearing a byte, word, and long word. So basically we're seeing the clear instruction. Okay. Now we're going to do the swap instruction, and swap is quite a useful instruction. You will use it a lot, especially on the Amiga. So we are going to move the 0 into the 3, and now we're going to swap the 0. So you're going to see that the AA00 becomes the high word and the FFF becomes the low word. And then we move that number, but the word, okay, what is in the 0 into the 4. Okay, now this is something that you will use a lot on the Amiga. Let's say you're setting up the bit plane of the Amiga bit planes. Normally you have in the copper, you have the register value, so E0 and E2, and you have to populate this one. So you need the address of a bit plane, okay? And we're going to pretend that the address of the bit plane is this one, okay? The 1, 2, 3, 4, 5, 6, 7, 8. So we get the table. We are getting the number into the 0. We get the address of the table, I meant. And now we get we move the word that we have in the 0, so the 5, 6, 7, we move the word, yes, we move the word that we have in the 0, the 5, 6, 7, 8, into 8, 0, but let me see. Into the, okay. Yeah. This should have been, I'm going to run it again. Because we are moving the low word, no? So the low word should be here. And the high word, sorry, with the mouse pointer. We are moving, so line 72, we are moving the low word, 5, 6, 7, 8. So this should be not 2, should be 6. And this one should be 2. Okay? So we are moving the low word, and then we are moving the high word. So let me correct this. It should be, because on the Amiga, this is what you will do. So we get the address of my table into 80. We get the number into the 0 of the address of our bit plane, whatever we're going to move into the 0. Now we move the low word, okay, into the register E2, okay, and we swap, and as you can see, the number got swapped in the 0. Okay, so in the low word, we have 1, 2, 3, 4 now, and we move 2. Sorry, we move the 1, 2, 3, 4 into 2, into here, basically where I'm indicating. And to show you what I mean, let's do my table. So you can see 0, 0, E, okay, and now we should have the high word, which is 1, 2, 3, 4, right? 1, 2, 3, 4. Now we have 0, 0, E2. So again, down here, you can see we have 0, 0, E2. And then we have the 1, 2, 3, 4. Okay, so this is the high word. Okay, now we have the 0, 0, E2, what we have here, and we should get the low word. So 5, 6, 7, 8. Okay, so because it's always like this. This is the high word, this is the low word. So this is why I said here, we are moving the low word of the number, of this number that where we had 0, right? Because we are doing that, then it needs to go here, because this is the high word. Yes, low words. So in the Amiga, okay, in the Amiga, and this is what this register, okay, the 0080 is the, you have to specify the value of a bit plane, which is a 32-bit number, okay, so 4 bytes, and this register 80 is the high word, and this register is the low word. So when we move.w did 0, 6 bracket 80, okay, we moved the low word here. Sorry, I thought I was pointing with the mouse. The value the first one here, line 72, okay? We moved it. Yeah, this is correct. 1, 2, 3, 4, 5, 6, 7. So 6 and 7 means it's the 6th byte, and 2 is the 2nd byte. That's what it means. But the value is written at the 2nd byte and at the 6th byte. The value at the 2nd byte, or where it starts the 2nd word, the high word, is at location 2. Where it starts the low word is at location 6. So we are moving this value. So if you do move.w did 0, what do you think is going to move? No, it's not bits. This means the positions. So this is byte 0, byte 1, byte 2, byte 3. It's the index, no? So this value, the 2 or the 6, is the index from, it's the offset, let's say this, from the label, from my table. That's what it is. Hence why 2 and 6, and 2 is the high word, 6 is the low word. Is that clear, SP? Guys, do not blame, okay? Do not blame Docster or anything, okay? These are examples or files that he did or he helped me out with, and everyone makes these type of mistakes. So it's, in a way, it's good to show them, and it's not to, you know, also he was learning at that time, so it's obviously common things that beginners do. So in a way, it's a good thing that I'm showing them. Hello, Proton. So let's do the next one. So here we are going to cover the exchange instruction and the not. Okay, so we have a number into the 0, and we have another number in the 1, okay, which is 20. And we're going to exchange the 0 and the 1. So basically what's in the 0 becomes 20, and what's in the 1 becomes 10. Also, it's just a swap basically. Again, we're moving a value into 80, and we're exchanging the 0 with 80. Again, we're moving a number into a 1, and we are exchanging 80 with a 1. We're moving a number into the 0, and we are negating, we are notting, okay? And remember, this is not negate, it's a not. And we are only working on byte here, so the 0. And here, no, Proton, I don't have the mini or maxi. I somehow skip them. Let's put it this way. And now we are doing not of what's in A1, and it's a word, okay? We are doing a not of what's in A1 offset 1, okay? And it's a long. And we're doing the same thing, not one. And we're doing the same thing on B. I hope I didn't crash my Amiga here. I'm realizing I'm working on address 80. Sorry, address 20. Not a good example. Anyway, so yeah. So we are going to work with signed and unsigned numbers, but to be fair, it's a whole text. The text, I have read it before to you, and I do not want to go through it again. It is in the previous episodes. We are just going to see the example, okay? So we cleared the 0. We move what we have into, we move 4 as byte into the 0, and we negate the byte in the 0. Remember, negate is 2's complement, so whatever we have, if it's 4, it's going to become -4. And then we return it back. Basically, if we negate again, we get the 4 back. Okay, so this is to show the negate instruction more than anything. So we're going to do the OR, test, and XOR, okay? Sorry, AND, OR, test, and XOR instructions. So we're clearing the 0. We are moving byte 3 into the 0. And we are ORing immediate 30 into the 0. So remember, OR, when we have a 1, the output is a 1. Now we're going to end what is in the 0 with CF, okay, and we get 03. We clear the 1, we get the address of test bits. The .l is confusing, but it means the same. It's always a long address. And we're going to move quick 7 into the 0. We're going to move what we have in a 0 plus offset or index the 0, which is 7, into the 1. And we XOR what is in the 1 with FF, which becomes 7F. Now we're going to do the test example. So we move 1 into the 0. We test the 0. Is it not equal? It's not. So we jump into the label not 0. We move quick the 0. We move 0 into the 0. We test the 0. Is it 0? I was going to say something, but I'm going to leave it out. But I'm pretty sure someone noticed this. And we branch if it's 0 to is 0, okay? And we return, basically. So we're going to talk about the bit set, bit clear, bit change, and bit test, okay? So bit set is you test for the bit and you set. Bit clear, you test for the bit and you clear. Bit change, if the bit is 1, you do it at 0, and if it's a 0, it becomes a 1. And bit test is you test for the bit. So let's start the example. So we cleared the 0. We test bit 2 and set bit 2 into the 0. You can see it became 4. You can see, oh, yeah. Thank you, thank you, thank you. Okay, so we cleared the 0, okay, and we set bit 2, so we had a value of 4, okay, in the 0. Then we're going to set bit 3 into the 0, which makes it a C. We're going to change bit 2, okay, so we're going to switch it from 1 to 0, and that gives us an 8. Now we're going to clear a bit clear. So bit 3, okay, we are going to clear it, and that means that the 8 becomes a 0 in the 0, of course. Then we're going to change bit 3 again. So we're going to make it on. So we have 8 again. And then we're going to bit test. Okay, we're going to test if bit 3 is set or not. If it's not equal to 0, so that means it is set. Okay, we jump. And we jumped to the loop. Now, this part I cannot really debug it, but basically Docster is using bit 6 of the register BFE001, which is testing for the left mouse button on the Amiga. Because we are doing debugging, it will take me some time, so I'm going to press the left mouse button, but it will take me some time to exit. Actually, it took it immediately. But yeah, that's what it did. So 11A. Uh, 11A 11A talks about bit shifting. Okay, we're going to use the did I skip one? Give me a second. No. Okay, so I'm in the correct one. We're going to move for C into the 0. Then we are going to rotate left. Okay, so rotate means shift the bits to the left. Okay, so we shift them by 1 to the left. But it also means that what goes out comes in. Okay, so we get 98. We're going to do the opposite way, rotate right. So what comes out? So, okay, one thing that I didn't say is on rotate left. Okay, what goes out from the most significant bit goes into the least significant bit. Okay, that's what happens. Rotate right is the opposite. Okay, and also what I need to say in relation to the rotate left and right, what goes out goes, so from the most significant bit goes to the least significant bit for rotate right, and rotate left, okay, is from the, sorry, rotate left is from most significant bit to the least significant bit, and rotate no, I already did this. I do not want to go into the details of all this, SP. This was lesson 9, if not mistaken. So I do not want to go to all the stuff. But one thing that I will show, okay, just to not to confuse you, so maybe it makes it more understandable. There. So you can see, rotate left, what goes out comes in on the other side. Okay? And rotate right, what goes out, so the least significant bit goes into the most significant bit. So that's all you need to remember. Also, there's a copy of it in the carry flag, okay? As you can see in both cases here. That's what you need to remember. Whether it's byte, word, or long word, it's always the same. So, now we're going to do ASR and LSR. And I'm just going to show you again that in the book. In the book, in the so at 0 in ASL, a 0 is always entered into the least significant bit. What is in the most significant bit goes into the carry flag and in the extended bit. ASR, okay, it's a bit different. And there's something else that I need to say. The most significant bit, if it's a 0, we continue to get 0 in the most significant bit. If it's a 1, we continue to get 1. So sign preserved or sign extended, whatever you want to call it. What is in the least significant bit goes into the carry or into the extended bit. Why they are called arithmetic shifts? Because these handle signed numbers. That's why you have that. This is the difference between ASL and LSL and LSR. Logical, we have logical and arithmetic, which we will do, but I'm just going to remind you for those that missed. We have LSL, this is logical. So at 0 is always in, so this is the same as ASL. At 0 always goes in, and the most significant bit goes copied into the carry flag and extended bit. The difference is here. Arithmetic shift left maintains the most significant bit, while LSR, you always get at 0 in the most significant bit. the output, the least significant bit always goes to the carry and the extended. This was lesson 9, guys. And honestly, there's lots of text to read, but I do not want to go through it. Watch lesson 9. So, back to the Amiga. So we move CC into the 0. You can see the bits there, okay? And we do an arithmetic shift right. So we are shifting to the right, okay? And the most significant bit is maintained. We are moving 20 into the 0, and we're doing another ASR. And the most significant bit is also maintained because we have a 0. We are doing an FF into the 0, and we are shifting it to the left by 1. Notice we get a 0 this time in the least significant bit. You need to, I mean, this is just, as I said, these are just revision. In the previous episodes, I mean, we went into detail of this, okay? I covered every one of them one by one. So notice also something that I should mention, the flag, okay? The negative flag is set because of the sign of the number that we had. So here we have the logical version instead of the ASR. So we cleared the 0, we move 4B into the 0, and we shift it to the left. 4, you can specify.
Thanks for the raid.
Oh, Duncan. Oh, Duncan, thank you for the raid. Duncan, we logical shift left, but we have in the 0 by 4. You can also specify by how much you can shift. Okay, if you don't specify, it's always by 1. But if you specify, you can specify by how much you want to shift. Here, we're going to shift, logical shift left by 6, also what we have in the 0. Now we're going to shift by 1 because we didn't specify what is in the 0 by 1. And you can see it's 5800 now. So logical shift left, what we have in the 0, what we have in the 1 with the 0. It shifted with 0, so the 0 had 0, so it didn't do anything to the 1. So 6, we're going to shift 6 left the 0. Then we're going to shift by 1 the 0. Yeah. And now we are shifting the byte in the 1 by how much we specify in the 0, which is 0. So it remains the same. Yeah. Now we shift left, but it's a word. So, and it's a memory location. I am hesitant to do it. I'm skipping it. I should have thought better about the examples because, you know, we are dealing with memory locations which we didn't specify. It should be a label, that one. But anyway, it's not an issue. And we are shifting what's in 80, that value, but the word by 1. Yeah. We are clearing the 0. We are moving 4b into the 0, and we are logical shift right now, so we are moving the opposite way. So it's like dividing by 2. Yeah, that's why I skipped it. It's a gamble. I didn't want to do that. I should have corrected that. So I skipped it by mistake. That should be a label defined in the program, not some address in memory. Let's do this from the beginning. So again, we're clearing the 0, 4b into the 0, and logical shift left by 4 what is in the 0, okay, and we get bit 0. Then we logical shift left by 6 what is in the 0, and we get to see, oh wow. Then we logical shift left by 1, and what is in the 0 becomes 5800. Now I moved 1, I corrected this, moved 1 into the 0, and I'm going to shift left by 1 what is in the 1, okay, and get FE. That makes more sense. Now I'm going to shift what it's in my label, okay, by a word, okay. So basically whatever that is, I'm going to shift it by 1. And now we are shifting by 1 also what is in 80, and but we are incrementing 80. We will look at my label in a minute. That I initialized it to 0, okay? So we're clearing the 0. Now we are going to do LSR. We cleared the 0, we move 4b into the 0, and we logical shift right by 2 what is in the 0. So shift right is like dividing by 2, okay, each time. So, and it depends by how much each shift is division by 2. But if you do 2 shifts, then it is by 4, 3 shifts is by 8, etc., etc. So clear the 0, we move 20 into the 0, and arithmetic shift left this time. So the number is treated as signed by 2 what is in the 0. I mean, we shift by 2, but actually we are dividing by 4, okay? That's what it means. We're clearing the 0, we're moving 81 into the 0, and we are doing arithmetic shift right by 2 shifts into the 0. Now you can see that I edit my label. So if I do my label, you can see that because it was at 0, it remained 0. 1, 2, 1, 2, 3, 4, 5, 6. Yeah, because it's a long. So I should have, yeah, you cannot see it, but give me a second. I will show it to you in a minute because the example I did, it's not 100% clear. So I'm going to correct it and show it to you more clearer. How the heck did how the heck did this 2000 escaped me? So in my label, I moved FF, okay? So, and the rest of the bytes are 0. Actually, because this is a long, let me correct it again. Okay, like that. So let's read it again. So I'm just going to do the part of my label, this part. So I shifted left what's in my label, okay? So now you can see it's still the same. Did I not specify by how much? Ah, man. How it lost it me, this one. No, you know what? I'm going to delete that. It's not a good example. Yeah, because asking for trouble, that example there. And I'm also going to delete this one. Yeah, not both of them, not good examples. No, it has nothing to do. It just no, Proton, not, it's not a question of dividing or multiplying or things like that. It's a way of showing the instruction, but those were not good examples, so I just deleted them. Yeah, it's better like this. Because to be honest, I did this is revision, and ASL is, yeah. Did I say that? Okay, then. Oops. Oops. Sorry then. Thank you, Proton, for highlighting that. No, I thought he was referring to my label. No. Okay. Thank you for that, Proton. Yeah. I made even a cuckoo myself. You see how much I got confused because of that? I do not know how that example escaped me. Anyway, let's continue. So, again, this example, okay, all these, we went through them, okay? I'm not going to read all the text. I'm just going to execute the instructions to remind you. We are clearing what is in the 0, we are moving B2 into the 0, and we are rotating left. And we are working on byte size. We are shifting by 2, okay? By 2 bits, okay? what we have in the 0 and becomes CA. We're clearing the 0, we are moving B2 into the 0, and we are rotating right this time by 2, okay, the byte that is in the 0, and that becomes a C. No, X is not part of this series, Proton. I had already explained it to you, I think, in one of the episodes earlier. I skipped the X bit, and I said it from the beginning that I'm not going to cover any instruction that deals with the X bit. So, we're just going to do the jump, JSR, branch to subroutine, and RTS. Now, branch and jump are the same, but jump can jump to any place in memory. Branch can only jump within a block, within a -22768 and +22767, okay? And within the same section. It cannot cross sections. Jump can go anywhere. Same thing, there is JSR and BSR. JSR can jump to anywhere in memory, can jump to any subroutine in memory. Branch to subroutine, BSR, can only jump within a section, first of all, and again -22768 and +22767. So keep that in mind. I'm talking always on the 68,000. We are moving 0 into the 0, and we are moving where the jumps are. Okay, and we are moving, okay, and this is relative. The jumps, so we are pointing to the address here at the beginning into A5. Now, we're jumping to what A5 points to. And it is jump 1. As you can see, we have a table here and we jump to jump 1, basically to the label where we have jump 1. We move 1 into the 0, we jump back to main, okay. Did I skip 1? I have to start it again, guys. I think I pressed the wrong key, because this is the thing. So we are here, okay. We move 1 into the 1, and then we jump into main 2. Okay, so now main 2, we are adding 4 to A5, so we are basically going to jump into the address of jump 2. Remember, hope you can see them. These are long. If we add 4 to A5, it means we're going to jump 2, okay, which is this one. There you go. I thought something is not right. These examples, both of them escaped me. I don't know how I did not. Damn it. Guys, I'm sorry, I'm going to skip this example. We are just going to do a revision of all the addressing modes now. So move quick. Remember, move quick works on long. and it's going to clear all the registers in this case. So now we're going to we are going to clear them all, clear the address registers using the sub. Okay, so notice that the address registers are also being cleared. You can do it in many ways. I just showed one way of doing it. Now we're going to use the immediate mode. So we are moving immediate values into the registers, whether it's byte, word, and long word. And now we are moving negative numbers, okay, into D3, D4, D5. Just notice that the M flag will be set, okay, for all three. Now we are just copying from byte, word, and long using data register and direct from D0 to D6. Okay, so you're going to see D6 changing to the values of the what was in the register D0 to D2. Again, we're going to move what is in D3 to D5 using byte, word, and long words into D0. And notice again the M flag. Address register direct. Okay, so we're going to move an immediate value into A0. We're going to move long address into A1. Notice that although you moved in the first one, although you moved 400, okay, you can only specify word or long word, no bytes, okay. A2 sub long A2, so we cleared A2. We moved 8000 to A2. We here I'm just showing the addressing modes, guys. I should maybe have done this the first one before I showed the other examples, but it became the last one for some reason. So we are also clearing A0 and A1, but this time is word. Sorry, moving what is in A0 into A1, and we just moved a word. And now we are moving what is in D2 to A3. This part is quite long, I have to say. This is my writing. It's not Docster's example, this is my example. We're moving a byte into label 1, and we're moving what we had in label 1 into the 0. And you can see the 45. We're moving this number into the 3, into label 3, sorry. And we are moving what we had in label 3 into the 1. But notice that we moved along, but we copied only a word. Okay, so we're clearing the 0. We are moving 45 into label 1, and we are moving word now, label 1 into the 0. We are moving 1, 2, 3, 4, 5 into label 2. I should maybe show the labels, no? Because I'm still showing the labels are here, okay? So we are moving dot long with the 1, 2, 3, 4, 5 into label 2. And we are moving the word, okay? What is in label 2 into D1? We are clearing D0, D1, D2. And now we're going to use address register indirect. So we're moving the address of the label 2 into 80. We are moving the value 89 in what's in 80, okay, which is the address of A2. And now we are moving what is in 80, but word into D0. And you get the 8901. Notice I always have the values that should appear in the debugger there. So we're moving the address of label 2 into A1 again. We're moving word 1, 2, 3, 4 into D1. And we are moving D1, okay, this time is long, into what's in A1. So at label D2, at label 2, we get 0, 0, 0, 1, 2, 3, 4, okay, because it's a long. And then we move word. This is, I'm changing the sizes intentionally to make you aware and to be careful, okay? What we have in label 2, okay? So we're moving a word and it becomes into the D2. So we're going to copy the high word of label 2 is 0, and we're going to copy 0 in D2. Address register increment and decrement. So we're going to have label 1 into 80, and now we are just going to go through a series of increment and decrements basically. So we move 89 into 80, but we increment 80, okay? So notice the 80 is going to increment by 1. Now what we have in 80, we move it into D1. And it is always a byte. Then we move 10 into 80 and we increment 80. Then we take label 1 and we move it into D5, and we take label 2, the address of label 2, and we move it into A1. Now we take the value 1, 2, 3, 4, and we move it into D1. It's always it was a word, sorry, I forgot to say that. And now we move word, what is in D1, into A1, but this time A1 is incremented not by 1 but by 2, okay? And now we move long, what we have that number into A1, and it is incremented by 4, okay, because it's a long. So notice the value of A1 is going to increment by 4. Now we're going to move the label into the 2, but the contents, okay? So the first 4 bytes, what we have in label 1 into the 2, as you can see. And now we're going to move the address of label 1 into A2, just to show the difference, okay, between a label when you put a hash and not. And now we're going to move a word. So we are going to increment A2 by 2, okay? And the contents of A2 will be into the 1. So now we did, that was increment. We're going to do the decrement part now, pre-decrement. So we get label 3. It's a relative into 80. We move 89, the byte, okay, into 80, and then we decrement sorry, we decrement 80 and then we move the byte. Then we move what's in 80 into the 1. You can see the 89. Now we move 10 into 80, but before we decrement. Now we move label 2 into the 5 and the contents. And we get the address of label 2, but relative into A1. Again, we move word 1, 2, 3, 4 into the 1. We move word what's in the 1 into A1, but first we decrement. And we move dot long 1, 2, 3, 4, 5, 6, 7, 8 into A1, but first we decrement. Address register indirect with displacement. So now is when we have an address register and we have a number before, no? So we take the address of label 2 and we move it into 80. We take we move 89 into the address of 80 plus 2. Okay, so offset of 2. And now we move what we have in offset of 2 and 80 into the 1. We move byte 10 into 4. So this time is minus 4. Okay, because you can specify it can be a positive and it can be a negative. Okay, into 80. So minus 4 from 80. So it was label 2. Minus 4 of label 2 is what? Label 1, right? And we move what's in 80 into D5. And you get the 1, 2, 3, 4, 1, 2, 3, 4, 8, 9, 8, 9. Now we get the address of label 2 again into 80. We move dot word 1, 2, 3, 4 into the 1. It's hiding me the instruction. So we move what's in the 1, 6. So we went 6 from A1, okay, from offset of A1. I forgot what A1 was pointing to last, but and then we move that value into minus 2 from A1. I believe A1 was pointing to label 2 also. Yeah, it was pointing to label 2. So we went 6 and then 2 back. So it's like we went plus 4 from label 2, so which is label 3. We move 4 into the 0, and now I'm showing you index, address register indirect with index. And notice the index can be either a positive, the first one, I'm talking about the number here, positive or a negative. You have the address register and the data register. Data register can be word. And basically you do a summation of all. So A1, you add the 0, which is 4, but actually we go minus 4. So we stay what the value of A1 is. This is just to show you that you can do these things. And that's basically it. Okay, so we did address registers. Sorry, the addressing modes. Okay, we're nearly there. So I have the exercises. I'm going to go through them. The people that submitted the exercises were Hound Dog and SP175. They are all on Discord. I didn't correct any one of them. I just love them and thank you very much for participating. But I'm going to go through the exercises here. So this one, we said what will be the value in the 0, okay? And to comment the code. So the first one is clearing the 0 and the 1. Then we're moving 10, and notice it's a decimal number, okay, into the 0. Then we multiply by what is in the 0 by 5. Then we move 40 into the 1. We divide what's in the 1 by 4. Exchange the 0 and the 1, so we exchange them. And then we sub what's in the 1, which is the 32 minus 49, minus the 49, which becomes 1, because that was a 50. The 32 was a 50, right? And then we multiply what's in the 0 by 10. So it becomes 64. And then we add 1. We add the what's in the 1, which becomes into the 0. And of course, the 0 is 65, which is 101 in decimal. So that's one. So this one, there is an illegal instruction. I think you know which one it is. It will execute it in my case because I'm running on a higher processor, but there is MULU, okay? That is an illegal instruction on 68,000. So because it's a dot long. So I'll move 10 into the 0. We multiply what's in the 0 by 5. It didn't give me an issue. Actually, let me see if I assemble. Look, it gave a warning. It is a 68020 instruction, okay? So be careful. So that was the answer. Let's say that the mulu.l. We move byte, we divide. I mean, the assembler should stop. Okay, it didn't stop because I'm using a 68030. But that was the instruction, the legal instruction. So here you have to comment and say what is the result of the 0. Now this is ambiguous. So we're saving the registers. We're moving that number into the 0. We're swapping it. We are moving that number into the 0. We are swapping the 0 again. And then we are restoring. So what is the address of the 0? It depends. In our case, it was 10. And we got it back. Basically, it depends. That was the trick behind it. These you haven't seen, but I'm going to do them. So basically, again, what is the value of the 0? So we clear the 0, we get the address of the data in a 0, we move 5 into the 1, so we get 80 plus 5. Okay, so if you count 5 from data, you should know that you're going to get 20. So 0, 1, 2, 3, 4, 5. Okay, because we count from 0. Last one. You have 5 into the 0. Remember, move quick is always long. And what is negate by the 0? It's minus 5. No, so you get the value of FB. Remember, it's 2's complement. Okay, guys. I think we did finish the series. I'd like to thank Docster for the help. Apologies for one of the examples that really escaped me. I did check all the examples of Docsters, but as you can see, even I can make mistakes. However, I still would like to thank him and much appreciate for all the help in relation to this. Actually, he pushed me in doing this series, and as I would have never done it, I think. And I think it was beneficial. I mean, even to me, to a certain extent, it was. Because although I covered most of the stuff in the book, so yeah, thank you, Docster. Much, really appreciated for the help. It was a series that as I was saying, I did not plan, but it did help me because sometimes you know things, but then you don't look at the detail of them. That to do this series, I had to go into the detail. So things that escape you or things that you think you know, but then you look into the, sometimes the devil is in the detail, when you start looking at the minor things. And yeah, it was one of those things. Although I didn't cover all the instructions, as I said, I skipped those that use the extended bit and some other non-important instructions, let's say that. Who knows, maybe I will do them in future, but right now I do not feel like, let's say that. I have no plan. But what it made me, one thing that it was never clear to me, okay? The instructions, which are really 68020 and 68030, and those that are really 68000. I used to get confused. I always need to look at books to make sure that what I'm doing right, but now I think I learned that, or at least I hope I learned that, because I mixed many times, like the same issue that Docster did I had the same issue personally. So it does help. It did help, and doing such a series is it was very beneficial, not just to you guys, but also to me. So thank you very much. In the next episodes, it will be all game gems. I have, sorry, all games, not game gems. I do not plan of doing any more streams related to teaching, let's say that. There will be the odd one, but I do not plan of doing any more things, except I just want to do games, basically. And that's hardcore. I don't think it's hardcore because I do simple games, but I just want to do games, basically. If there is something that I think that is worth doing a stream on, or mentioning in a stream which is related to development or to coding, I will mention it. But yeah, from now on, it is definitely game coding and Amiga game coding. Sometimes maybe I do 64, but it will be Amiga game coding. So once again, so guys, thank you very much, and I hope to see you next week with my next series. It will always be called Let's Make an Amiga Game, and it will be volume whatever. It will be volume 4, since now right now we are doing the Tanks game. So that's the next series. Let's Make an Amiga Game, and it will be episode 2 of the Let's Make an Amiga Game, volume 4. See you guys, and thank you. Bye bye.